Hello and welcome to the first lesson in my course on number theory. Today we're going to be talking about divisors, the division theorem, and Euclid's algorithm. So let's first talk about divisors. What do we mean when we say 4 divides 28? Or equivalently, you might write it as this. Well, in general, that means that we can write 28 as 4 times some constant, where this constant has to be an integer. So in this case, we might say that k equals 7 works here, which means that 4 is a divisor of 28. So we can write out the set of divisors of a number. For example, the set of divisors of 12 is 1, 2, 3, 4, 6, and 12, if we're just looking at positive divisors here. And similarly, we can list the divisors of 8. You can see they're 1, 2, 4, and 8. Each of these numbers divides 8. If we want to talk about the greatest common divisor of two numbers, for example, 8 and 12, what we need to do is look at these two sets and see what the greatest number they have in common are. So the numbers they have in common are 1, 2, and 4. And 4 is the greatest number out of this set of 3 common divisors. So it must be the greatest common divisor. So now let's talk about the division theorem. It simply states that given two integers, a and b, with b not equal to 0, there exist unique integers q and r such that a equals b times q plus r, and r is greater than or equal to 0 and less than b. Q is called the quotient here, and r is called the remainder. You might be familiar with that. So now we're going to try to go about proving this theorem. To do that, we consider the set a minus b times q, where q is an integer and a minus bq is greater than or equal to 0. For example, here we see that if a is 28 and b is 5, we end up with this set going 3, 8, 13, 18, 23, 28, 33, and so on. And we claim that r is the minimum element of this set. So first we show that any valid remainder must be part of this set. That's pretty easy, since if a equals b times q1 plus r1, then r1 equals a minus b q1, which is obviously part of S. Now we'll assume that the minimum value of S is not equal to r1. Then we must have in our set an element less than r1, which, as you can see here, has to equal r1 minus b. But this would contradict our theorem, which states that r is between 0 and absolute value of b. If r minus b were a member of the set, then r would have to be greater than the absolute value of b. This lets us conclude that the minimum value of set has to equal r, which gives us a unique value for q and r, and therefore we have proven the theorem. Now we'll start looking at the Euclidean algorithm, and the fundamental part of it is this theorem, which states that if a equals b times q plus r, then the greatest common divisor of a and b equals the greatest common divisor of b and r. As an example, we see that the greatest common divisor of 12 and 8 is the greatest common divisor of 8 and 4, because we can write 12 equals 8 times 1 plus 4. And we're just looking at these two numbers now. To prove this, first let d equal the greatest common divisor of a and b. What we first want to show is that d is a divisor of r as well. So if we write a equals bq plus r, then we want to show that d divides a minus b times q. Since we know that d divides both a and b, we can substitute a equals d times a1 and b equals d times b1, where these two are integers. Then we substitute a and b into our expression up here, and we get d divides d times a1 minus d times b1 times q. and we can factor this as d divides d times a1 minus b1q. And this is obviously true because d divides itself, and it's going to divide itself multiplied by any integer as well. Therefore, we can conclude that d divides r. Now we want to look at this the other way, where we say E equals GCD of B and R. Now we can write A equals B times Q plus R. Now we can let B equals E times B1 and R equal E times R1. And doing what we did before, where we substitute B and R into the equation here, we see that A equals E times B1Q plus R1, which implies that E divides A. So what we've essentially proven is that if E equals the greatest common divisor of B and R, then it must divide A as well. And if D is the greatest common divisor of A and B, then it must divide R as well. So what we want to show in the end is that E equals D. So we'll assume first, for the sake of contradiction, that E were greater than D. Well, we know that E is the divisor of A, B, and R by this above statement here. And that tells us that E divides both A and B. Now we know that D equals the greatest common divisor of A and B, but we've just found a divisor greater than D that also divides A and B, and that is a contradiction. And similarly, we could go the other way. If we assume that D were greater than E for the sake of contradiction, then we know that D divides A, B, and R, which means that D divides both B and R. And that means that we found a greater divisor of B and R than E, which we thought was the greatest common divisor of B and R. Therefore, this also reaches a contradiction. And by that, we can conclude that E must equal D. So going back to the statement of Euclid's algorithm, we've shown exactly what we want, which is that the greatest common divisor of A and B equals the greatest common divisor of B and R. So now we want to see why this is useful, and it will involve something called the Euclidean algorithm, which is just a repeated application of the theorem I've just shown you. Let's say you were trying to calculate the greatest common divisor of 270 and 600. Well, the first thing you can see is that you can divide 600 by 270 to get 270 times 2 plus 60, where 2 is the quotient and 60 is the remainder. Therefore, we can equivalently write this number as the greatest common divisor of 270 and 60. Now this time we can divide 270 by 60, so we can write 270 as 60 times 4 plus 30, where 4 is the quotient and 30 is the remainder. And therefore we can equivalently write this number as the greatest common divisor of 30 and 60. Now when we reach this point, we can't go any further without getting a remainder of 0, which means we're done. And our answer is just the smaller of these two numbers, which happens to be 30. So we'll finish off with a couple problems. This problem is from the 1985 AIME. The question is, the numbers in the sequence 101, 104, 109, 116, and so on are of the form a sub n equals 100 plus n squared, where n equals 1, 2, 3, and so on. For each n, let d sub n be the greatest common divisor of a sub n and a sub n plus 1. Find the maximum value of d sub n as n ranges through the positive integers. So I encourage you to pause this video and try to find out the solution for yourself before I go into solving it. So the solution goes as follows. Let a sub n be 100 plus n squared and a sub n plus 1 equal 100 plus n plus 1 quantity squared. Then we know that d sub n equals the greatest common divisor of 100 plus n squared and 100 plus n squared, n plus 1 quantity squared, which we can write out as this once we expand it. Now by Euclid's theorem, we can subtract 100 plus n squared from this side, and this number will be equal to the greatest common divisor of 100 plus n squared and 2n plus 1. So once you've reached this point, we want to divide 100 plus n squared by 2n plus 1 again. But it's going to get messy if we just do it directly because we'll have fractions involved. So one way to approach this is this side is odd, and the greatest common divisor is going to be unchanged if we multiply this side by a power of 2. So let's multiply it by 4. Then we get the greatest common divisor of 400 plus 4n squared and 2n plus 1, and now we can divide this. So here we write it as the greatest common divisor of the quantity 2n plus 1 squared minus 4n plus 399 and 2n plus 1. Now we can subtract 2n plus 1 or any multiple of it from both sides. And that gives us the greatest common divisor of negative 4n plus 399 and 2n plus 1. Now if you think about it, we can actually do the reverse as well, and we can take this and add a multiple of 2n plus 1 to it and get the same greatest common divisor. So we'll do just that to end up with a number on one side. And when you do that, you end up with the greatest common divisor of 401 and 2n plus 1. Now we're trying to find the maximum value of d sub n as n ranges through the positive integers. And as you can see, if we choose, for example, n equals 200, then we'll end up with the greatest common divisor of 401 and 401, which equals 401. And we can't actually go any bigger than this, since the greatest common divisor of these two numbers has to be less than or equal to 401, which means that this is the maximum possible value, and that's our answer. Now we'll look at problem 1 from the 1959 IMO. It says, prove that 21n plus 4 over 14n plus 3 is irreducible for every natural number n. An equivalent way to write this problem is that the greatest common divisor of 21n plus 4 and 14n plus 3 equals 1. If you're thinking about why that is, if the greatest common divisor is anything other than 1, then we could divide both the numerator and the denominator by that divisor, and then it wouldn't be irreducible. But as long as the greatest common divisor is 1, there's nothing we can divide the numerator and denominator both by to get integers. On the first step, we subtract 14n plus 3 from 21n plus 4, and what we end up with is the greatest common divisor of 7n plus 1 and 14n plus 3. And then for the next step, we subtract 2 times 7n plus 1 from 14n plus 3, and we end up with the greatest common divisor of 7n plus 1 and 1, which is obviously 1 because nothing divides 1 except for 1. And this tells us that this fraction is irreducible for all natural numbers n, which means we're done. I hope you learned something about divisibility and the Euclidean algorithm in this video. I hope to see you next time. Bye.